In the year 1666, Isaac Newton, in complete isolation, developed three laws of motion. His second law of motion stands as a pillar of science today. It's worth noting that Newton changed 2,000 years of physics history, where we were living under the reign of Aristotle's foolish ideas of motion, and Newton single-handedly, well, maybe with the help of Galileo a bit, upended those notions and set forth three laws to describe all that he observed. His second law, F equals ma, is a statement that really mathematicizes his first law of motion. Recall, his first law of motion talked about changes in velocity being associated with forces. Changes in velocity, of course, are accelerations. And so here, in his second law, he explains exactly how changes in velocity are related to the forces that cause them. Recall also from his first law that the mass was significant. When the mass went up, the change in velocity became less. And vice versa, when the mass was smaller, the change in velocity, the acceleration, was bigger. This one law, F equals ma, explained all the things that Newton was suggesting in his first law. Note, by stating his law in this way, he has, in effect, defined what the force is that he was referring to in the previous law. So let's examine what we can learn about the force based upon this equation. First of all, let's take a look at the units. We know that kilograms have a standard unit, mass has a standard unit of kilograms. Acceleration has a standard unit of meters per second squared, meters per second. And so therefore, force, if we obey the equal sign, must have units equivalent to kilograms times meters divided by seconds squared. This is a fine and correct unit, however, it's a bit cumbersome. So, in honor of Mr. Newton, we abbreviate this particular combination of units simply with a capital N, must be capital since it's a last name, and so a Newton will be a kilogram times a meter divided by a second squared. We will always refer to forces in newtons. The second thing to observe from this equation is that, if you remember, acceleration is a vector quantity. Acceleration has a direction associated with it. And since mass does not, mass is simply a scalar, it's just a number, so many kilograms. If we abide by the equal sign, this tells us that the direction of the force is in the same direction as the acceleration. These two quantities must always be equal. The question is, how do we determine the force if we don't know directly the mass and acceleration? Clearly, if you do know the mass and the acceleration, you can determine the force. So let's say that we have an object of unknown mass for the time being, but let's take a look at some forces. Remember that it's suggested here that forces are vectors. So let's imagine that we have, let's say we have two forces acting on this object. Let's say we have one force that runs off this way, and a second force that comes back this way. So let's say there are two forces acting on the object. Let's give them numbers. Let's say that this force is a force of 6, 6 what? 6 newtons. Let's say that this is a force of 2 newtons. Okay. And the question is, what value should we use for the force if we've got these two forces at play? You should be aware that in most cases there are many forces acting on an object. So the question is, what value do you use for the force in this equation? Well, your intuition probably serves you right. If you see 6 newtons in this direction, 2 newtons in that direction, the total force in this picture is equivalent to simply 4 newtons to the right. So this force, 4 newtons to the right, is neither the 2 nor the 6, but it's the combination of the two. We speak of this force as being the net force. So if we want to clean up this equation a little bit, we should say that in truth it's not any old force, but it's the net force that predicts how this mass will accelerate. Let's try our hand at a few other diagrams and see if you can determine the net force. Okay, let's look at some more examples with simple numbers so we get the idea. But let's finish off this first one. Let's say we do know the mass, and let's say it's 2 kilograms. Our net force is 4, based on the picture, 4 newtons to the right. Our mass is 2, so that means our acceleration must also be 2, because 2 times 2 for the acceleration, 2 meters per second squared, times 2 kilograms is 4 newtons. So 2 meters per second squared. I won't write the units on the future ones. Let's take a look at our next diagram. Supposing we have a force of 6 newtons this way, 2 newtons that way, 3 newtons up, and 3 newtons down. Let me put those numbers on there. 2, 3, 3, and 6. What is the net force in this situation? Well, we still have the same 6, the same 2, but we've now introduced these other two forces, 3 up, 3 down. The up and down forces will cancel each other, leaving us just the same 4 newtons to the right again. And if the net force is the same and the mass is the same, then the acceleration should also be the same, 2 meters per second squared. Now let's say we have the same 6 to the right, we have the same 2 to the left. Let's put those numbers in there, 2 this way, 6 that way, and we'll keep even the same 3 down. And the question is, now what is the net force? This one's a little trickier. So we've lost just one of that extra 3 Newton force to the top, so that we lose that cancellation. So how do these forces combine? Well, the 6 and 2 are going to combine in the same way to give us 4 newtons to the right. However, we still have 3 newtons down. How do we combine 4 to the right and 3 down? If your intuition tells you that you end up with 5 newtons, you are correct. How we get to 5 is because the 4 newtons is what we have to the right, the 3 newtons is what we have down, and recall that force is a vector. So it adds, we find the combined force by adding the individuals, and 3 plus 4 equals 5. This is a famous 3, 4, 5 Pythagorean triangle. 3, 4, 5. It obeys the 3 squared plus 4 squared equals 5 squared rule. And so, what would the acceleration be on this 2 kilogram object feeling a net force of 5 newtons? Well, we can use our Newton's second law. Net force is 5. Mass is 2. Divide both sides by 2, and we get A equals 5 halves, or 2.5 meters per second squared. 2.5 A times mass of 2 equals 5 newtons of net force. Let's take a look now at a slightly simpler case. Supposing we are looking at an object with just a single force on it. Supposing this 10 kilogram object experiences just a single force of, let's say 98 newtons. What's the net force in this case? Well, this is the easiest case of all. If there are no other forces to consider, then in the case of a single force, the single force is the net force, 98 newtons, and the acceleration would be, well, let's see, net force is 98, mass is 10, divide both sides by 10, and we get an acceleration of 9.8 meters per second squared. The case of gravity. So that tells us that if an object is falling at a standard rate of acceleration, 9.8 meters per second squared, we can deduce that that single force is the force of gravity. Okay, here comes 2 questions now to see if you have understood. In our first picture, we have a 3 kilogram object experiencing 3 forces. Using F net equals ma, can you predict what the acceleration will be? You might want to pause the video while you think this through, and then I'll show you the answer. So go ahead and pause. And now the answer. So we've got a 10 and a 2. That should give us an 8 running this way, a 6 going down. So that means that we've got a 8, a 6, and we're looking for the net force here. You should remember that it's going to be the sum of these two. And so this is a 8, 6. We can do Pythagoras with these two, and you will find if you do that 6 squared plus 8 squared is equal to 100, which is 10 squared. This is really the 3, 4, 5 triangle in disguise. 3, 4, 5, double everything, 6, 8, 10. So 10 newtons is our net force. So we've got a 10 for our net force, 10 newtons. We've got a mass of 3. So the acceleration, if we solve for a here, divide both sides by 3, and the acceleration equals 3.33 meters per second squared. Next question. This one's a little different. Here we've got a 4 kilogram box. It starts at rest and then accelerates to a speed of 6 meters per second in a time of 3 seconds. And the objective is to find the missing force. So pause and see if you can solve this on your own. And then when you have a solution, unpause. Okay. So the first thing you need to do is figure out the acceleration. Since we're ultimately going to be using F net equals ma to solve this, you'll want to first see if we can get a value for the acceleration. So using one of your equations of motion, probably v final equals at plus v initial. If we use this equation, we can solve for the acceleration. Our initial velocity was 0, because it said it started at rest. Our final velocity was 6. Our time was 3. And so you can see our acceleration is going to come out as 2 meters per second squared. And that's the value that you would use in F net equals ma. So let's take a look. Let's make a little path here. So we know that the mass is 4, the acceleration is 2, which comes out to a net force of 8. So we now know the net force is equal to 8. So now let's examine our picture up here. We've got 12 newtons this way. We are looking for a net force of 8. So we can see by inspection that this force has to be 4 newtons. 12 minus 4 gives us the 8 that we want. 12 minus question mark was supposed to equal 8. In solving for the question mark, we get 4. Okay, so those are some beginning problems with Newton's second law. Next step is to get better, or actually begin, seeing forces properly. So far, all these forces have been given to you, 12 newtons, 4 newtons. Where did they come from? It's going to be your job to determine what the forces are. You have to be able to see and identify the forces instead of having them being given to you.